Why do people not email me back? This is frustrating. Someone, like, there was a big panic with the grades going in yesterday with one student, and, like, didn't respond to me for an entire day, and then someone else emailed him and he responded in, like, 10 minutes. Feels real bad, man. Team ask questions. No. I mean, I'll talk about, like, general. I'm not just gonna, like, do the whole homework during class time. That's what office hours are for. We can talk about, like, one or two or something maybe, but yeah. Alright, so I've gotta, yeah. Do this. We'll get our screen. It's weird how it seems to go out when I'm not using it, but then during stream. Alright, Reese, mute yourself. As much as I hear my own voice a lot. Or we could never do series again. That seems unlikely. Alright, well. Good, clean family fun. Hold on, I need to see something. Does this... Or is it only on my laptop? Yeah, it's only on my laptop. That's interesting. These are the important things, guys. You gotta emote at a high level. And gotta enable better Twitch TV. Wait, better Twitch TV? You're failing me. That's fine. Alright. I think I need to enable it on my channel then. RIP. Okay, so let's do math instead of watching me attempt to use emotes. It's a very silly cardigan. It's not a cardigan, man. Is it? What is the definition of a cardigan? This is like a sweatshirt, but a very light one. But, alright, we can debate cardigans and the definition thereof afterward. Okay, so with this, we basically were done wrapping up most of the Taylor series things. Sweater that opens in the front. Yeah, this is a sweatshirt. I don't know if that counts. I mean, it's got a hood. I don't know. Anyway, same as a dope color. So, wanted to give one more use of like Taylor series before we start talking about error terms, which is what our class prep was on. That was a little bit shorter class prep in general, right? So, yeah. So, it's not that, I'm pretty sure. Alright. So, last time we had just finished with finding the exact value of that like one series and solving for x on the other one. So another useful thing, and there are a couple ways to do this, but sometimes it's more useful if something has a weird derivative. But just like a very simple example where you could use more than one method, perhaps. Right, like you ostensibly could just figure out what's going to go on by using L'Hopital's rule here, right? Because what do we get with this limit? You would do 0 minus 0 over 0. And so you would get an indeterminate form. You would think, all right, I can use L'Hopital's rule. And in this case, I think these are probably about equal in terms of the amount of time they would take. You could do 3 steps, right, and get the denominator down to degree 0 with L'Hopital's rule, so like 3 straight applications. Or we can use the fact that we know the power series for sine. So remember that sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, right, you get all of the odd powers. And, gosh dang it. is this? There it is. Okay, should be back now. All right, I just want to make sure I am on the same. Yeah, okay. It didn't go out at all this morning. Right, so if you look at this numerator then, well, we just subtract x away, right? Sine x minus x is just take away this guy and leave the rest. All right. So then what do we get afterward? Well, we divide by x cubed. So now we get this. That's a 3. And we get negative 1 over 3 factorial, or negative 1/6, plus x squared over 5 factorial minus x to the 4th over 7 factorial, and so on. So if I take the limit as x approaches 0 here, what am I going to get? You tell me. Right, well, negative 1/6, but yeah, exactly. Like all of these guys, right, all have x. And so all of those go to 0. And so we get negative 1 over 3 factorial, or negative 1/6. And so this can be a more convenient way of doing some limits that would otherwise be difficult. So it's just kind of another use to keep in mind. Yeah, there's not that much more. Like on most of these, right, you could do L'Hopital's rule. It's just that you wouldn't have to. And so I think, did I put something on the problem set like that? I think that'll be on the next one. Yeah, I'll put a couple of limits where you can use the power series instead of L'Hopital's rule. But basically, it may or may not actually save you time. Whoa, what? Problems, sorry, like homework. Is problem set from other classes make you that scared? Yeah, just homework, like the one that'll be due Monday. Is what you get for being friends with people in algebra and topology. Okay, so yeah, I don't think this is worth spending a ton of time on. It's more just like, okay, see it here, see it on a couple homework problems, but it's probably not the only way to do those limits, and so it's just more of a like, hey, this is another application of power series if you choose to apply them that way. But one of the more useful ones is, well, I guess not necessarily the Taylor series, but the Taylor polynomials, right? So on 11.7, if you have that sheet out, on the second page at the top, or in the class prep video for today, I talked about the error term, right? Because basically, for instance, e to the x, right, is 1 plus x squared over 2, x cubed over 6, or 3 factorial, and so on. But that's a lot of terms to do, right? And the point is, this actually is true for all x, right? Like, they're literally equal because it converges for all x. But, if you want to use this to estimate, right, say like e, let's do like 1 over e, okay? So I want to know e to the minus 1. Well, I can go ahead and like literally do this, right? Negative 1 squared over 2, negative 1 cubed, right? And I can keep going forever and ever. And I know this is going to converge, right? Because this is basically an alternating, it is an alternating series. And the terms are going to 0 because of the n factorial down there. And so like this will converge, but I already knew that anyway. But this isn't that easy to actually find out what it converges to, right? That's often the issue. And so if I want like an approximation of e to the minus 1 or 1 over e, I want to know like roughly what that is. This doesn't really help me a ton. But I can estimate it by lopping off most of the terms, right? So maybe I just stop here, right? And I call this like P3 of x would be just up to the degree 3 term. Right, so this is my third degree Taylor polynomial instead of series, because it's finite degree. And this is, again, for e to the x centered at 0. And so if I want to know like how much error would I expect to get here, right? So this is where I would have to look at some interval, right? So I basically am wanting to see P3 of 1 should be roughly e to the minus 1, and my question is, what is the error? Because that's pretty easy to actually plug in, right? Like P3 of 1 is just P3. What am I writing? P3 of 1 is equal to 1 plus negative 1 plus 1/2 minus 1/3. These guys cancel, and so it's 1/2 minus 1/3, or 3/6 minus 2/6, so I get 1/6. So that's like super fast to compute, right? We did that in like 20 seconds once I figured out how to write what I was saying. And the question is, right, like how close is this to the actual number 1 over e? So we figure that out by this formula, right? So we need I to be some interval, sorry, P3 of negative 1. Oh boy. Yeah, I'm plugging in negative 1 at each of these. Some interval containing the thing you want to estimate and your center. And so the easiest interval to do would just be the smallest thing containing both, which would be like the closed interval from negative 1 to 0. And then the idea, right, is the farther away you are from the center, the worse your approximation is going to be. Our hope is that like negative 1's not that far away from the center 0, so this should be a pretty decent approximation pretty quickly. So the third degree might actually not be too bad. If I did like the 20th degree, I'd probably be like correct to a whole bunch of decimal points. So then looking at our little like formula there, right? So we want this bound. In general, we have this, and I think I mentioned in the video, right? Like this should remind you of finding the error bounds for like Riemann sum approximations, right? You had like midpoint, trapezoidal, or left or right, and we had these constants that showed up, right? And it was all about bounding like the first or the second derivative. And we called it like k1 and k2 to be the first or the second derivative, and this is kn plus 1 because it's the n plus first derivative. So this guy is like some constant upper bound. And for us, f of x is e to the x. And so all of its derivatives are itself, right? And so this is also e to the x. And the key is that this has to be true, constant upper bound. I should put like on your interval I, right? It doesn't have to be true everywhere. It's just where you're focusing. And so for us, like on negative 1 to 0, what is my upper bound on e? What's the biggest e to the x can be on the interval from negative 1 to 0? Yeah, it's 1, right? Because once we get negative powers, we're dividing by stuff. And so e to the 0 is actually the biggest. So it's e to the 0, which is equal to 1. Nice and convenient, just like the one on the class prep. And then what does this tell us? So this means my kn plus 1 should be equal to 1. And so then Taylor's theorem says that the error, again, I'll write the general situation first and then our specific situation. So the error between the nth degree polynomial at x and the actual, or geez, sorry, this is not the derivative, actually f, and the polynomial is less than or equal to kn plus 1 over n plus 1 factorial times the distance away from the center to the n plus 1th power. Okay, so you can kind of see again that this would be in the numerator over here, so the farther away, the bigger this part is, and so the more like error you could get. So for us, what do we have? So we have x is -1, we have x naught is 0, and so we have f of -1, or e to the -1, minus p3 of -1 is less than or equal to, we said kn plus 1 was 1, over n is 3 here, so 4 factorial, times the difference between these, which is, right, like -1 minus 0 to the 4th. But we don't really need to do that, right, because that is 1, its absolute value. So this basically goes away, and so our error is less than or equal to 1/24, or 4 factorial. And so we're already within, 0.05, just with our third degree. So already between 0.04 and 0.05 error after just 3 terms. So I mean that's not too bad, right? Considering like it's equal if you do infinitely many terms to only take up to the third degree, like that's pretty good. Questions on that process? We can talk about. Well, we'll do a couple of examples here. We can do number 9 first, probably, or we can talk about the class prep one as well. Good. I'm not used to this silence from you guys. Alright. Well. Class prep one? Okay. Yeah, we can do that. So that was sine, right? Yeah. I think it was actually just straight up sine, not sine of x squared. Okay, so this was use Taylor poly to estimate sine of, so again, centered at 0 to estimate sine of 2 within 1/100th, or 0.01. Okay, so in this case, again, we want to basically, right, like find the degree, find how far you have to go down the line to get within 1/100th of what you want. So our goal is to find n, so we actually have to apply the general case here, right? Whereas on the previous one, I just said, like, use the third degree and see how close you are. So here we have, we need a bound. So f of x is sine of x. So the question is, the derivative, what is the bound for this? Less than or equal to question mark on, again, we want to choose our interval. What interval should we use if we want to estimate 2 and it has to include the center 0? That's not an interval. Oh, that's the bound. Yeah, I understand. Okay, so yeah, you guys answered both of them. So, right. So the interval is going to be from 0 to 2. That includes the point we want and the point we need, the center. And then our bound, right, like our derivatives just cycle, right? We get sine, cosine, negative cosine, and then it loops back, right? So all of these are bounded above by 1 in absolute value. And so this is another one where you can just use 1. Okay, so then Taylor's theorem says that sine of 2 minus my nth degree Taylor polynomial at 2, that error is going to be less than or equal to, so my kn plus 1, that's 1. So I'll just make that clear. This means kn plus 1 is 1 over n plus 1 factorial times x is 2, x naught is 0 to the n plus 1. Right, so this is our error, and so rewriting that error like this, we want this to be less than or equal to 0.01, right? We want to be within a hundredth. For me, I don't know. Different people looked at this different ways from what I saw in the class prep. Some people are actually like going ahead and doing the division and seeing like when that compared to 0.01. For me, if I'm just doing it by hand, I prefer to actually multiply. So like I view this as 1/100th, and I multiply over. So this is the same thing as saying like 100 times 2 to the n plus 1 is less than or equal to n plus 1 factorial. Right? I basically just like cross multiply. And they're all positive, so I don't have to worry about like flipping the equality or inequality. And then you just kind of start checking. I mean, it's a little bit guess and check. I can see that this one's going to be way bigger at the start, so maybe I go a few down the line. I check like n equals 5. Then I get 100 times 2 to the 6th, which is 64. So this is 6400. Whereas this guy is 6 factorial, which is 720. So this is way bigger, so that's not good. All right, I get a little bigger. But this guy's always just multiplying by 2, right? So you don't have to think too hard on this. So this is 12,800, or 128 times 100. And this is 7 factorial, which is 5040. All right, this is still bigger. And then at n equals 7, you're good, because this is now 25,600, and this is times 8 from the previous one, so you get 40,320, and so we got what we want. So we know that once we hit n equals 7, our error is going to be small enough. And then anything past there, you're just going to get more and more accurate. And you can see, by the way, like how quickly that error term is going to go up, right, if you are farther away. If this was like 3, for instance, I wanted sine of 3, your 2 to the n plus 1 becomes a 3 to the n plus 1, right? And so like you're going to be multiplying by bigger and bigger things on the left side. It's going to take higher and higher n to get there. Because we know that factorial eventually grows faster. Well, I mean, it's always growing faster, but eventually will be bigger than any exponential, but it may take a long time to get there. Any questions on that one? All right. I think you're prepared then for number 9. I want you guys to try number 9 together. You can unmute yourselves in the Discord chat. I just want to kind of hear your thoughts. I can maybe scribe some things, but I wanted to hear you guys kind of talk about it. And I'll just shut up. You can talk. No, that's right. So you're looking for this. So why is your kn plus 1, 1? Yeah, what's your interval? Yep. But note, that's only because this is like that negative power up top. If it was e to the 2x, it would be at 1. Here, we can talk about that in a second. I'm not sure. Yes, Caleb. That is correct. Okay. Yeah. Yeah. I'm writing down what you're saying, yeah. Yeah, that's why I have this guy. Right, because your center is 0. So it's like 1 minus 0. Yep, and so here, just we don't have to spend like a ridiculous amount of time on this, but yeah, you just plug stuff in. I think it's more than that. Is it, or is it any? Is that the exact one we did last time? Yeah. It's Reese's. I think this is the one. I think n equals 6 works. Whereas n equals 5 would give us just 720. Cool. Oh, yeah, you probably just said 7 because that's what n plus 1 is. That makes sense. Okay, so I have a question. What if I want e squared within 0.001? Yeah, because x is -1, so here I is -1 to 0, and so e to the -2x but we want to be careful here because this is just f of x. So like this is true. So this is less than e squared. But what about the nth derivative? Oh, this is why, yeah, no, we screwed up on the last one. Sorry, this, yeah, I had it written down. N plus 1th derivative. We were just looking at bounding the function. So here, actually we should just, this example will be good enough. We just need to redo this. So no, k n plus 1 is not this. It's a nice thing about being able to erase. There's got to be a better way to do this. Sorry, so this is true. But Taylor's theorem, yeah. I mean, that's why I initially paused. I thought I had the wrong example, and then I just realized I didn't realize the mistake. So we want to look at the n plus 1th derivative of x when f of x is e to the -2x. E to the -2x. So what is the n plus 1th derivative of x? How could we find this? And if you don't see it immediately, I would just recommend taking a couple derivatives and you'll see a pattern really, really fast. Okay, yeah, so let's take a derivative then. So we need the chain rule, right? So it's -2 e to the -2x. What's my next derivative? Yep, and so what's my, do you already see the pattern? What's this guy? It's not going up by 2. Yeah, so it's by -2, right? So very close max, but yeah, -2, right? We're switching sign every time because of the -2x. So it's -2 to the n plus 1 e to the minus 2x. Right, because the power of -2 matches the whatever we have for the derivative. So, what's my bound on this guy? On 0 to 1. So you're right, the biggest would happen at 0 still, it's just that we have this extra term coming from the derivative, right? So it's definitely going to be smaller when x is 1, because we'd be like dividing by e squared. So it is going to happen at 0, and it would just be 2 to the n plus 1, because we take the absolute value. So the negative goes away. So it won't be 2, it will be to the n plus 1. Because that power doesn't go away. Yeah, because yes, this one is harder now because of this. So when we take it to our formula, right, so now we're ready for that. So we want f of 1 or e to the minus 2. Minus Pn of 1 is less than or equal to, okay, so our k to the n plus 1, boom, over n plus 1 factorial times, and then this guy is still like 1 minus 0 to the n plus 1, so that's fine. And we want this to be less than or equal to 0.001. And so, more simplified, we want this. And again, this kind of becomes personal preference, right? Where if you like fractions, you're good. For me, I like to cross multiply. And it looks a lot like the previous thing. You just have to go farther, right? Because we have 1,000 here instead of 100. And so I did the work beforehand. So at n equals 8, right? Because we know it already has to be at least past 7, because that one we've already seen from the previous problem. So at n equals 8, you get 1,000 times 2 to the 9th is 512,000, whereas 9 factorial is a mere 362,880. But then if you go one more to n equals 9, 1,000 times 2 to the 10th is large number, 1,024,000, and 10 factorial, well, that's easy because I just add a 0 to the 9 factorial. And if you match your commas up, you see that one's 3 million, one's 1 million, and so n equals 9 is what you would need. Yeah, sorry about the screw up and not picking that up the first time. But yes, you have to be careful, right? So moral of the story is, don't forget that it's the derivatives, not just the function itself, when you're bounding. Okay? Questions? All right. So let's go ahead and finish off the worksheet here. So this one, just to get like a new kind of function, wanted to deal with the square root, so we haven't seen that in a while. The heck? Okay, so here I tell you which polynomial to use. So we're going to look at p3 of x for square root of x, and the main reason I want to do this is we want to look at something not centered at 0. So why can I not? So I'm going to claim here that like not only did I choose not to center it at 0, I actually cannot center this at 0. Do we see why? Yeah, but why? Yeah, exactly. So it's all about the derivative, right? So can't center at 0, right? So even just one derivative, f prime is 1 over 2 root x. F prime of 0 doesn't make sense, right? And so it just can't work. So we center somewhere else. I chose 16 because 16 is a pretty easy thing to take a square root of, and because I specifically want to estimate root 17, and that's the closest perfect square to 17. Okay, so this one we can actually get the number out if you want, but we can see what the error would be first. So the error, right, is like f of 17 minus p3 of 17 less or equal to stuff. So we need to figure out, so this would be k4 over 4 factorial. Yeah? Because we can do better. Right, so like this is our x, not our x naught. Yeah, I can hear you. I think the delay is longer right now. Right, and so this would be like 17 minus 16 to the n plus 1 as well. So we need to find out what k4 is, right? So in this case, it's not fun to take like a ton of derivatives here, but remember we only need to get to this fourth derivative. So let's go ahead and take a few of these guys. So f prime, 1/2 x to the negative 1/2, f double prime, negative 1/4 x to the negative 3/2, triple prime, 3/8 x to the negative 5/2, and finally the one we want here to bound is negative 15/16 x to the negative 7/2, or negative 15 over 16 x to the 7/2. All right, so the key point is remember that your interval is from 16 to 17 in this case, right? Our center is at 16, we want 17. And so, like, this is a nasty looking number. Looks bad. But it's not too bad to bound because think about where this is going to be biggest. So if you divide by more, you're going to get less, right? Remember, we're talking about absolute value, so the negative sign doesn't matter here. And so it's going to happen, so this maxes out when x equals 16. And so we would get k n plus 1 is equal to this. I'm just going to go ahead and say like 4 to the 7th. I'm going to go ahead and take the square root of that 16. Or sorry, this is k4 specifically. And that guy's very small. It's something like 10 to the negative 5th. So that means you're going to be accurate within about, or for the first 5 decimal, for first 5 decimals, first 5 digits after the decimal. Okay? So that would be your error term there. Yeah. How could you actually get this P3 of 17? So we know how close it would be. How would you actually find the real polynomial? Yeah, we just plug into that formula. So the important thing here is to remember your center is not 0. Okay, so it's going to be, a0 plus a1, not x minus 16 because it's centered there, plus a2 x minus 16 squared. Or yeah, I guess it is just that. The a's include the factorial division. And then this, and then basically a0 is, well, that is just plug it in, right? So it's square root of 16, or 4. a1, you do 1 over 2 root x, or 1/2 x to the minus 1/2 at your center, all divided by 2 factorial. Right, a1, how am I getting that? I'm doing f prime of 16 over 2 factorial, right? And so this guy ends up being 1 over 2 times 4 times 2. Okay. A2 is f double prime of 16. Why am I doing? It's not over 2 factorial. I'm sorry. That would be a2. This is just 1 over 2 times 4. So 1/8. This is over 2 factorial. Derivatives match the factorials. Okay, the second derivative I did earlier, right? It was like negative 1/4, 16 to the negative 3/2, or square root of 16 cubed over 2 factorial. And basically you just get like 1 over big number, and you would plug it in. I would probably give you something that looks a little bit nicer on a test, but yeah, on a homework problem, basically you would just want to go through this process. But we're basically out of time, so I figured doing a whole bunch of arithmetic with these derivatives is probably not what you want to see after class is technically ended. But I can hop on the working together if you want to talk about homework problems or whatever. Our office hours are technically now. So I'll go ahead and end the stream, and we can talk about whatever.